This video is about the last video in thermochemistry, and it's about calorimetry. Calorimetry is a really important concept. It's definitely a lab that you need to be familiar with because it shows up a lot of times on the AP exam, either as a multiple choice question or as the lab question in the free response. We see it showing up a lot. So be really comfortable with the calorimetry calculations and the concept of the exchange of heat between the system and the surroundings. So what is calorimetry? You've probably heard of the word calorie. Calorie we associate with food. So it's the energy. A calorie is a measurement of the energy in the food. So how do we measure that energy? We measure it in the form of heat flow. So here's what a calorie is. A calorie is the amount of heat required to raise 1 gram of water 1 degree Celsius. And that has been measured, and it is defined as 4.184 joules. So this is a really important number. You're going to see it associated a lot with this calculation, but that's the definition of the heat required to raise 1 gram of water 1 degree Celsius. And we call that the heat capacity. So, or specific heat capacity. So what is the specific heat capacity? It takes 4.184 joules to raise 1 gram of water 1 degree Celsius. So how do we measure this heat for calorimetry? We use this expensive lab device where we just take 2 coffee cups, and they are going to be styrofoam coffee cups, insulators, and we're going to perform our reaction inside the coffee cup, and the other thing that's going to be in the coffee cup is going to be some water. And so the water is going to be the thing that we're going to measure. So we're going to use a thermometer, and we're going to measure the amount of heat that is either absorbed or released by the water. So imagine this is your system, this is your little reaction, and if the reaction is exothermic and it gives off heat, the heat is going to go into the water. And then as the heat goes into the water, the temperature will go up. The converse could be true also. If the reaction was endothermic and therefore took in heat from its surroundings, the heat would leave the water and go into the reaction, and then the temperature would go down. So in a calorimeter, we measure the heat flow basically indirectly because we check the temperature of the water, and by looking at the change in the temperature of the water, this will allow us to measure the change in the temperature of the reaction and determine the enthalpy of the reaction. So it's just, again, about an exchange of heat between the system and the surroundings. In this case, we're going to use water as the surroundings, and we're going to use something else, a reaction or a salt or a piece of metal, as the system that the water is going to either absorb or release heat to. So how do we measure the heat flow? There is a calculation. This equation right here you will find on your equation sheet. Q equals mc delta T, or MCAT. Q is the heat. Now keep in mind, Q and enthalpy aren't the same thing yet. They're not the same thing. They have different units, so we're just going to be calculating heat. This is usually in joules. And so M in the MCAT part is for mass. That's the mass of the solution, which is going to be in grams. C is the specific heat of the solution, which we just talked about is going to be joules per gram degree Celsius. And depending on what you're talking about, it might have a different specific heat. Everything has a different specific heat, but the one that we most commonly use is water. And then delta T is your change in your temperature. And remember, deltas are state functions, so it's the difference between the final temperature and the initial temperature. So make sure you subtract that correctly, because signs are really important, and that's where you'll mess up your signs if you don't do that part correctly. So let's look at an example. So we are going to heat up some water. We're going to take 300 grams of water, and we want it to go from 22 degrees Celsius, somewhere close to room temperature, to 98 degrees Celsius, almost boiling. So imagine, we have a pot, and in the pot we're going to put some water, and then below the water we're going to add a heat source. And so the question is, how much heat do we need to add to that water to change the temperature to from 22 degrees Celsius to 98? So all we have to do is plug all that information into the Q equation. So 300 grams of water, and we know the specific heat of water, which will always be given to you, is 4.184 joules per gram degree Celsius, and we want the temperature to go up 76 degrees Celsius. 98 minus 22 gives us positive 76. So we want the temperature to go up. So how much heat do we have to put in? Do the calculation and look at this. Watch the units. They'll cancel out. You have grams on the top, grams on the bottom, degrees Celsius on the bottom, degrees Celsius on the top, and you are left with a unit of joules, which is a unit of energy. And so we have to put in, that's what the positive is for, we have to put in 95,395.2 joules of heat in order to get that water to go up in temperature to 98 degrees Celsius. So a couple of things to note when you are using a coffee cup calorimeter, because we're basically indirectly measuring the heat of the system, we are going to have to watch our signs. So we're comparing the surroundings to the system, and usually in a coffee cup calorimeter, the surroundings or is the solution, and that'd be like the water. And the system is the actual reaction, the thing that you're putting in the water. Sometimes this reaction becomes the solution, so just be careful. We'll talk about that in a little bit. Finally, the amount of heat released or absorbed by the reaction is dependent on the limiting reactant, and therefore you can calculate enthalpy by getting the Q of the reaction and dividing it by the moles of the limiting reactant. And we've done that. That's stoichiometry. The enthalpy is dependent on the limiting reactant. So we're going to have to take that into account when we're trying to get to the overall enthalpy of a reaction. So let's look at a couple of examples. First, we're going to do an example involving a reaction. So we're going to take 1 liter of barium nitrate, 1 molar barium nitrate, and it's at 25 degrees Celsius, and we're going to mix it with 1 liter of 1 molar sodium sulfate solution, also at 25 degrees Celsius, and we're going to mix those in the calorimeter. A solid forms, and the temperature of the mixture increases to 28.1 degrees Celsius. So, assuming that there's no heat lost to the calorimeter, and that the specific heat of the solution is 4.184 joules per gram degree Celsius, and the density of the solution is 1 gram per milliliter, calculate the standard enthalpy of change. So, let's just focus on the things that we know. First, what do we know? We took 1 liter of 1.00 molar barium nitrate. And we also took 1 liter of 1.00 molar sodium sulfate. So basically, what we did was we took our coffee cup calorimeter and we added those two things in there. So we put in the 1 liter of barium nitrate, and then we added the 1 liter of sodium sulfate. And so when we had 1 liter of this and 1 liter of this, now the total volume is 2 liters. And then all of those things mixed and reacted. Okay, and we checked the temperature. And what happened to the temperature? The temperature started at 25 degrees Celsius, and it went up to 28.1 degrees Celsius. So our change in our temperature is 28.1 minus 25, which gives us a change in temperature of positive 3.1 degrees Celsius. So what are the three things we know? Well, we know something about the solution. We know the solution is 2 liters. And they told us that the density of the solution is 1 gram per milliliter. So if we have a 2 liter solution, that would be 2,000 milliliters. And if the density of the solution is 1 gram per milliliter, then the mass of our solution is now 2,000 grams. And the only other thing that they gave us a piece of information for was the specific heat. And they said the specific heat is 4.184 joules per gram degrees Celsius. So look, we have our three things. We have our Q equals M. Well, there's our M, 2,000 grams. We have our C, specific heat, and we have our delta T. And so now we can calculate the enthalpy of this reaction. So let's calculate our Q with the things we know. We know our mass is equal to 2,000 grams. Our specific heat, 4.184 joules per gram degrees Celsius, and our delta T is positive 3.1 degrees Celsius. So let's calculate the Q. Q is equal to MC delta T, and we are finding the Q of the solution. And so that is equal to 2,000 grams times specific heat times positive 3.1 degrees Celsius. Now look what happens to your units. Grams go away, degrees Celsius goes away, and that leaves you with joules, which makes sense because this is a unit of energy. So Q of the solution is equal to positive 25940.8 joules. So that tells us something. The solution absorbed 25,941.8 joules. Where did that energy come from, or where did that heat flow from? Well, really the heat flowed from the reaction. So what does that tell us about the reaction? The reaction gave off that amount of heat. So keep in mind the Q of the solution is equal in magnitude but opposite in size as the Q of the reaction. Because really we're talking about this being, the reaction is basically the system, and the solution is the surroundings. And we can't measure the heat of the system, so we have to we have to measure the heat of the surroundings and then talk about its relationship with the system. So the Q of the reaction is negative 25940.8 joules. So now that we have the Q of the reaction, now let's calculate the delta H. Now keep in mind, Delta H is the enthalpy, so it's the amount of heat produced based on the limiting reactant. So here we go. We've got a little bit of information about our reaction. So since we had 1 liter of 1 molar barium nitrate, that means we have 1 mole of barium nitrate. And we had 1 liter of 1 molar sodium sulfate, and that means we have 1 mole of sodium sulfate. So looking at our balanced chemical equation here, we have to identify which one's the limiting reactant. Well, technically either is the limiting reactant. That amount of heat was produced by 1 mole of each of the reactants. So now we're going to calculate the enthalpy by dividing by the moles of the limiting reactant. And so here's what we need to be focused on. Enthalpy is equal to the Q divided by the moles of the limiting reactant. So there's the Q of the reaction that we just calculated. And here is 1 mole of the limiting reactant. And so we end up with negative 25,941.8 joules per mole. Okay? And so here's a note. When you're doing calorimetry, your answer for your enthalpies are going to end up in joules per mole, and that goes back to that specific heat of water. So you might have to change it to kilojoules, so just divide by 1,000, and that would give you negative 25.9408. With sig figs, we'll go negative 26 kilojoules per mole. And one thing to note, a negative enthalpy means the reaction's exothermic, and using logic, you should go back and know, well, that makes sense, because what happened to the temperature? The temperature went up, and if the temperature went up, the reaction is exothermic, we should end up with a negative enthalpy sign. So that is calorimetry using. Sometimes you have to do calorimetry where you only have one reactant, it's a salt. So you're going to take that salt and dissolve it. And in the process of dissolving the salt, it will either produce heat or absorb heat. And you're going to calculate it the same way. So the steps are, you're going to calculate the Q of the solution using MCAT. Then you're going to get the Q of the reaction, equal in magnitude, opposite in sign. And then you're going to get the delta H, which is the Q of the reaction divided by the moles of the limiting reactant. So you're going to have to work through those steps. If you do a lab, you're going to have to work those steps. The only difference here is what happens in the solution. So when it's dissolving, you add the masses. When it doesn't dissolve, you don't add the masses together. So let's look at this example and do some of the calculations. So what do we know? We put 4.25 grams of solid ammonium nitrate into 60 grams of water. The temperature drops from 22 to 16.9. We want to calculate the enthalpy. So first thing, get your mass. Add the two masses together. Second thing, get your change in temperature. This is a negative change. Why? Because the temperature went down. Third thing, calculate the Q of the solution. Mass times specific heat times change in temperature gives us the Q. Determine the Q of the reaction, because we just calculated Q of the solution. Equal in magnitude, but opposite in side. So the Q of the reaction is going to be positive 130.992 joules. Now we're going to calculate the enthalpy. We have a coffee cup calorimeter, and we're going to put some water in it, and we're going to add our salt to the solution. But what happens to the salt? Well, the salt's going to dissolve, and as the salt dissolves, it now becomes an aqueous solution. And as a result, the mass of the salt becomes part of the solution. So when you're dissolving, the mass is going to be equal to the mass of the water plus the mass of the salt. Notice that we have to add this here. Now, what if we didn't put a salt in there? What if instead we put a piece of metal in there? Like, I don't know, a spoon. So would the mass of the spoon become part of the solution? Well, if I put a spoon in here, is the spoon going to dissolve? No, but it still is going to absorb heat or release heat. So in that case, if you're dealing with a metal, the mass is just going to be the mass of the water, not including the mass of the spoon, because the spoon didn't become part of the solution. So just keep that in mind when you are doing these. Sometimes so what happened here? The ammonium nitrate became ammonium ions and nitrate ions. We know how many grams of ammonium nitrate we put in. We got to convert that to moles. Once we have that in moles, we know the Q of the reaction. It was positive 1,370. We know the moles of the salt that we put in there, 0.0531, and we just divide to get the enthalpy of the reaction. There should be a positive sign here. So that gives us positive 25,826.27 joules. Convert that to kilojoules if needed. Positive 25. Sig figs, positive 26. And look, this is endothermic. Why is it endothermic? How do we know? Well, the temperature dropped. It went from 22 degrees Celsius down to 16. And so that told us something that this reaction was endothermic.